Good morning, everyone. Online, am I audible to everyone?
Yes, sir.
Yes, sir.
So we are going to start the linear regression topic today. So this is the first of the algorithms. Now, before I get into the topic and the concepts, I just want to highlight a few things about the overall ML concepts. Okay, what exactly is? Now, you probably would have already covered this topic. How does prediction happen? What is ML? Okay. So this is about model. Now the next question is, what do you mean by the term model? What is this?
Test run.
Test what?
Test run.
Test run.
Test
Hmm?
train.
Test train. That is not a model. Model क्या होता है?
उसमें एक साथ दो शिफ्ट डालना।
See, you have a data here. Okay. Data, after you process the data, all the things, then you split the data in whatever ratio that you want. Sorry? Okay, let's say you're splitting the data into 70-30%, whatever ratio. And then you make this into a trained data. And this is the test data. You must have done this in the introduction session, isn't it? So ये train test करता क्या है?
जो अपने इनपुट और आउटपुट दोनों देने पड़ते हैं अपने को, उसको ट्रेन हो जाता है, उसके बाद हम टेस्ट देता है, अपने को प्रेडिक्शन करता है वो ट्रेन टेस्ट पे.
Okay. Okay, correct.
We first prepare a model using the trained data, and then we test that model using the test data.
Okay. Okay, fine. So when you say I take the trained data and build a model, right? Now the question is here, what is this model? ये model है क्या?
If we do some input, then it should give us predicted output.
Okay. But again, definition क्या है model का? What exactly is that model?
कितने की थी है?
Sorry? This model is nothing but the blueprint of the data, or you can say it is an equation, just like a function. Okay, function क्या करता है? It has some logic, isn't it? So logic is implemented using the data and it gives an output. Model is the same thing. तो यहाँ पे logic क्या है? It is the mathematical equation. That is why in machine learning there are two types of ML. क्या क्या है वो?
Supervised and unsupervised.
Supervised and
Unsupervised.
unsupervised. और supervised में भी there are two types. One is called parametric machine learning, and the other is non-parametric. Okay, your parametric है, इस पे you build equations. Okay, for example, linear regression builds an equation of the line y equals a plus bx. Okay, so ये y equals a plus bx is what?
Line. Equation of the line.
It is the equation of the line, correct? But with respect to ML, वो क्या है? Y is the value that you want to predict. X is the feature of your data. Okay, if you have multiple data points, you have x1, x2, x3, and every x1 will have a corresponding beta value or the weight of that particular value. Okay, so that is what is the parametric meaning. An equation is built. Okay, for non-parametric, we do not build an equation. Whenever we want to do a prediction, we train the model there and then do the prediction. So runtime पे training testing दोनों होता है. जैसे decision tree. Okay, now decision tree I cannot create a formula because it depends upon the data. ठीक है? Whereas linear regression, logistic regression में data is similar. ठीक है? यहाँ पे क्या है? Split based decision रहता है. Okay, so I cannot have a a formula to do it. Okay, so this is called non-parametric. Parametric में क्या क्या आएगा? Linear regression and logistic regression. Because in both these cases, I build a formula which is y equals a plus bx. Okay, this is the basic concept of the ML. Now, the next one is, how does prediction happen? ये आप लोगों ने किया था in the introduction session of machine learning, या maybe during the statistics first session.
Linear regression का model build किया था. House price prediction.
Okay. Then tell me, ये predictions, how does predictions happen? What is the underlying theory of the predictions? There are 2 points. The first is called IID. IID stands for independent and identical data distribution. Okay, and the second one is called generalization. So these are the 2 main ideas behind a prediction. IID का मतलब क्या है? When I have a data on which I build my model, which we call this as a trained data. Okay. Now the trained data is the data on which I build my model. So let's say this is my model. Okay. Now, using this model, I'm going to do the prediction or the forecasting. That is done on the test data. Now, the distribution of the trained data and the distribution of the test data, they have to be similar. That is what is called IID, independent and identical data distribution. Identical means what is there in the train should be there in the test. And why is it independent? The data of train is does not influence data of test. That is, test does not derive the data from train. Okay, train is a separate entity, test is a separate entity. They may come from the same population.
So if we divide a sample into 50-50, then it will be train test in IID.
50-50 generally we don't do. We generally take a higher percentage for training data. Because more the...
Then what is the significance of identical thing?
The distribution is identical.
Random.
Not the split percentage.
Okay.
For example, if I say the train data, the kurtosis value is 0.3. Okay. So in the test data, the kurtosis value should be similar to 0.3. It is this identity, not split identity. If train data is left skewed, test data will also be left skewed. Okay, that is the fundamental idea behind these predictions. Okay, and these are assumptions. So we have IID and generalization. Come. Yes, which batch are you? Sorry? Oh, you are in the wrong batch. I think it's the other class. Okay, now closely associated with IID is called generalization. So generalization means that what is there in the train, the assumption is it is going to be similar, test is going to be similar to train. Okay, so whatever pattern I see here, I'm going to do the same. I'm going to assume that the pattern is similar and the forecast or predictions can be made because it is similar in nature. So it generalizes whatever it has learned in the train and applies that principle on the test. Okay, just imagine you are taking an exam. Okay, let's say it's a maths exam pattern. Now you study a certain pattern. Okay, let's say the teacher or the professor gives you a certain pattern. This is how the exam pattern will be. Section A, 3 questions with some MCQs. Section B will be 5 questions with some MCQs. Third, part C will be all theory. A theory as in no MCQs. Okay, this is a fixed pattern. Okay, now you prepare your exams, for the exams based on this pattern. Okay, now what is the assumption? The exam will come in this same pattern, isn't it? Now, if there is any difference in the pattern, okay, will the performance be affected? It will. So the degree of how it will be affected, that varies. It may not affect also. Okay, but when you are preparing for a certain pattern, you assume that the same pattern will be there in the test also. So that is called generalization. Okay, so which is closely linked with IID. So what I see here will be also there in this. Okay, so these are the two techniques, the underlying factors behind a prediction of a model. Is this clear? Online, is this clear to everyone?
Yes.
Okay. Next. Okay. Now, I told you that generally the data is split into train and test. Now, why is the data split? Why can't I do a prediction without the splitting?
So we'll need to check if that model is built. We'll need to check the accuracy of that model. So if we make a model on the train data, then we can validate it on the test data.
So why do we want to split it? Why can't I build a model on the train and do the testing on the same data itself?
Because it will not give a proper measure, because you are building the model on the train data and again testing. So if it overfits, then you are not it is not a generalized model, then it is a particular model.
Correct. Okay, so when I take the data and train and do the testing on itself, okay, it does not give you a very good result. It may perform very well. Okay, because it has already seen the data. Okay. So again, coming back to the same example of a test. If I give you the question paper before the test, okay, will you perform well?
Yes.
Okay, chances are you will perform very well. But is that how you have to show your performance? No, your performance will be best, or it will be judged based on the questions you have not seen. Isn't it? So the same concept here also. The test data is known as the unseen data. Model has not seen the data, but it has only seen the trained data. It understands the pattern. So it assumes that the test data will also have a similar pattern. So it is blindly going to generalize whatever it has seen, and it does the forecasting or prediction. Okay. So usually when we get a data, it either comes as a standalone data, that is one complete set, which we split into train and test. Okay, this is what I think you have done. Split here. Now there are other variations that you will get. You will get a train data. You will get a test data. Alag alag. Okay, two different files, two different CSV or two different Excel files. Then you might also get a third variation where you have a train data. You have a validation data. And then you have a test data. Okay, so this is another variation that generally in industry you will get this kind of one. Now, what is the difference between this second one and the third one? Since you have already done some model building, you should be able to tell the difference between number 2 and number 3.
So in train and test, we usually train the model on the train data and apply it on the test, but not sure about the third one.
Yes, online, anyone? What is the difference between train test and train validation and test? Okay. No, it is not checking for errors. See, when you do a splitting of the data, okay, now train data will contain the features and it will contain Y, isn't it?
Yes.
Test data will also contain the X and Y. This is how you build the model. Okay, then you test whether the predicted Y and the actual Y, what is the difference? That is the error part. Okay. Now in the third variety, where you have train, validation and test, the train contains X and Y. Okay. This validation third one is actually the test. Okay. So validation will also contain X comma Y. Okay. So you are validating whether your model is good or not good. And finally, you have the test data, which contains only the X. It only contains the features and it is going to make the predictions. So this is known as the unseen data, that is future predictions.
So in train and test, we can validate our model on test data, right?
Which one?
In train test split.
Huh.
We can validate our model using the test data.
Train data.
Yeah, we make our model on the train data and then
The validation is done because you don't have 3 data sets. Okay, so how do you validate it?
using the test data.
No, because that is not a validation data. Technically, you're right. It is a validation data. Okay, but you have only 2 data sets. So you need to train also, validate also, and test also. Okay, so how do you do this? I'll come to that. Okay, that is called cross validation. So in the third technique, you have train, which contains features and Y, validation, which contains features and Y. So this behaves like number 2, train and test. Now you can only predict for the future, isn't it? You cannot predict for last week. You can only predict what is going to happen. So that is this test data. Now, how do you verify whether your predictions are good or not good? You can only do that in the validation, whether my model is good or not. Okay, but how do I know whether the model has actually performed well or not? After I get the test data. Okay, let's say that I want to predict the next week's temperature. Okay, starting from Monday to Sunday. Aaj kya hai? 25th. So from 26th till 30th of September. Right? 5 days. So how do I know my forecast is good or not? I have to wait till tomorrow. End of the day, I'll read the temperature. What is the day temperature? Let's say it is 30 degrees. How much did I predict? 29.2. Okay, then check. I had predicted so much, the actual is so much. So kitna error hai? 0.8. Okay, but to get to that level, I have to test it on the validation data. Whether given this data, how much is the error? And is that error consistent with the error in the test? Usko bolta hai cross validation. Have you done the concept of cross validation?
No.
But how did you directly get into model building without? These are very, very important concepts. Okay, this you have to know this. Okay. Any questions on this? Online, any questions on the splitting of the data? Why we are splitting it? Okay. Now comes the concept of cross validation. Now, cross-validation means I have my train data. I build the model. Okay. Now, how do I know this model is good? You apply this model on the test. Okay. And then verify the result here. Okay. This is the standard process. But before you apply this on the test, I want to do some kind of a validation so that I know that the testing results and the training results, are they consistent or is there a big difference? जिसपे model बना था, if I apply that model onto the same data, okay, I prepare, I get a question paper, I write the test using the question paper that I have got, check that performance with an unseen question paper. Same thing here, okay? So I build my model. Now I apply it on the same data. Will I get a 100% result here? Will it be 100%?
No.
Not necessary. Okay, chances of errors are high because it is a formula that gets built. And each time you cannot expect a 100% result. It could be highly accurate, but may not be 100% accurate. Okay. So I take the trained data, build the model, then using the same model, I train it, I test it. So this procedure is called cross-validation. So this is, there are different techniques to it. The most popular one is called K-fold cross-validation. Okay, now what is the meaning of K-fold cross-validation? Let me explain this with an example here. Now assume that my trained data size is 100. Okay, and the test data size is 20. Okay, so my model is built on this. Now, before I come to the testing part, I want to verify how the model is behaving on the same data. So this is called cross-validation. Okay, so what happens is in my trained data, I use a technique called K-fold cross-validation. So K is a positive integer. Ideally, it should be greater than 1. Okay. So now if I split my, let's say the value of K is 4. Okay, my K value is 4. So K equals 4 means my trained data, which is 100, is split into 4 parts. Okay, if the value of K is 5, the data trained is split into 5 parts. And each part will contain identical number of records. If it is not divisible, then one will contain less, others will contain the same. Okay, so let's assume that I am taking a value K as 5. Okay, so how will the distribution happen? So it will be 20. 20, 20, 20, 20, 20, and 20. Okay. Now value of K is 5. So what happens is now out of the n portions, one part is considered to be as a test data. The remaining portions are considered to be a training data. Okay, so let us say this is part 1. This is part 2. This is part 3. This is part 4. And this is part 5. Okay, so in the first iteration, my data will be split into 2 parts, where out of P1 to P5, 4 parts will come into training and 1 part will come into testing. Okay, so in the first iteration, I have training data. So what will be the parts? P1, P2, P3, P4. Okay, and what will be the test data? It will be the last part. So the same training data now gets split again into train and test. So 100 is split into 80 and 20. Is this clear? So this is 80 and this is 20. Now, the model is built on P1, P2, P3, P4 combination, and the testing is done on P5. And you get a result. So let's call this result of the first iteration. Okay. Now, the value of K is how much? 5. So that means every part will get to participate in the training and testing activity. Okay. So how many iterations will be performed? 5 iterations. So second iteration, what will happen? The data which was in the test will now come into train, and one data from train will go into test. Okay. Now if P5 comes into the training data, so that means one of the portions now will have to go to the testing. So if I take P1, P2 and P3. Now what will happen? Testing will have P4. Same process. Build the model on the training data, which is P1, P2, P3, P5. Do the prediction on P4 and I get a result. Let's call it R2.
So in the training, it is the combination of all 4
combinations. It's all a combination. So that's why given here 80. So 80, 20 will be same, but data will be different. Okay. Third iteration. Now P4 will come back to the training. So P4, P5, this will be P1, P2, this will be P3. And I have the third result. Ye result kya hai? What do you mean by result? Accuracy or error, depending on whether it is classification or regression. Okay. Regression mein this will be MSE, RMSE. If it is regression, if it is classification, it will be accuracy. Fourth one, P3 will come back, P4, P5, P1, this will be P2, and this will be result number 4. And the last iteration, P2, P3, P4, P5, and then P1. And the result will be R5. Okay, 5 iterations done. Now I take an average of R1, R5. So this will be the training error. Okay, so the cross validation is called the training error. Same model, when I apply it on the training data, what is the error and how different is this error from the testing error? Now I have the 80-20 here. Now I will apply this model onto my actual. This is the actual test. Okay. And now I'll get test error. So let's call this E1. Let's call this, I'll call this error of test. I'll just call this E2. So E1 is training error, E2 is testing error. So what do you think should be error 1 and error 2? Should they be identical or should they be different? They should be identical. Okay, it need not be the same. For example, if I'm taking a regression model and assuming that this error that I'm getting is MSE. MSE क्या है? Mean squared error. Okay, so MSE is E1, and let us say this number is 34.889. So what should be the testing error? It should also lie very close to this number. If I get an error of 35, is that good?
Yes.
Good, because the difference is very less. If I get an error of 12.5, is that good?
As compared to 35.
It is good, isn't it? Because errors are decreasing.
Yeah.
But if I get an error of 109.45, is this good?
No, it's not.
No. So here it is a violation of the IID. So this probably is happening because the training data is, or the testing data is different from the training data. Either the distribution is not proper, or there could be outliers, or there could be some other anomalies in the data. Is this concept clear? So we have to ensure that the training data, testing data, the errors are similar to each other. इसको बोलते हैं, this is called cross validation, k-fold cross validation, where k I have taken as 5.
तो उस मॉडल में करते हैं, उसमें जो अपने डेटा लेते हो और ट्रेन में सब जो आपने स्प्लिट किया है P1 to P5 वही ट्रेन पे यूज करेंगे ना मॉडल का.
नहीं, it's the other way around. Train is split into P1 to P5. जो ट्रेनिंग डेटा है, the training data size, let's say it is 100. Train data is 100. तो इस ट्रेन डेटा को हमने स्प्लिट किया है into 5 parts. That is P1, P2, P3, P4 and P5. P1 will have 20, P2 will have 20, 20, 20, 20. Okay, and they are all different records. Same records nahi hai sir. Split into 20 each. ठीक है? Online people, any questions so far? Okay. So now we can start with the linear regression model. Yeah, one more thing. For building a model, what should be the data types? Numeric and category. What are the other types that I can have? I can have a string data type and I can have date. Okay, now I am doing a linear regression model. If you have a string data and if you have a date data in your data set, what should you do?
Date can be converted into numeric.
Okay, date can be converted to numeric.
String into categories.
Strings to categories. So convert this to category and convert this to number. Any other answers?
I think both two categories.
Both two categories. Okay. So both two categories. Category or string mein, what is the difference?
Categories are limited combination of characters.
Good. Categories have limited number of entries, isn't it? If I have 100 records, the categories could be gender, which will have only 2 values, male, female. String carry.
It may have any combination of characters.
Right. So strings are generally non-unique characters, isn't it? First name, last name, okay, address, description. Okay, so these are non-unique. Maybe 2 people have the same first name or the same last name or even same first name, last name, but the chances are very less. So when you have a string data in your data set, what should you do? Is it worth converting it into a category? No. And what is the impact or what is the relation between your name and whether you will score 90 in your exam? Is there any relation? There is no relation, isn't it? So that means the entry or the feature called name has no relation, X has no relation with Y. So what should you do in that case? Remove it. So whenever you have any string data type in your data set, the first thing you should do is Don't consider it in your model building. Unless it is a category, because category is also a string. String is also a string, but category is a special type of string. So how do you convert a male, female into numbers? This is easy, isn't it? Wherever there is an M, replace this with, let's say, 0. Wherever there's an F, replace this with 1. Straightforward. Okay, so this is called, you can either use dummy variable, okay, or label encoding. Fine. Date. Date ka is actually depending upon the context or the data. What is the importance of date? You have to first see whether the date has any relation with the value that you're going to forecast or predict. Okay, for example, I want to find out, let's say sales. I want to do some prediction. What is going to be the sales in the next quarter? Okay, then I have, let's say, 500 records of orders, 500 orders. And every order will have an order date. Okay, order date, order amount. So in that case, do you think a date is significant to predict the sales? If yes, which portion of the date is significant? Is the month significant? Is the day significant? Or is the year significant? Okay, so that you can analyze and find out what kind of analysis you want. Because the entire date is of no use. Because today is what, 25th of September this year. So can I say 25th of September last year, we had the same kind of sales? Maybe there is a relation, I don't know. So you need to analyze that. If you feel there is a pattern, retain it. Otherwise, even date also, generally, we don't consider. Okay, clear? So these are the two things that you need to remember. What should be the Y variable? It has to be numeric.
So if the date is considered, then what data type should be considered about date? Sorry,
if the date is what?
If the date is to be taken into consideration, so
okay.
Does it
I'll answer
convert?
So if you have to take the date, if you feel that the date is important, then you should not do a linear regression. You will do time series. Okay, there is another statistical algorithm called time series analysis, where the data is time bound. Daily basis, weekly basis, monthly basis, quarterly basis, yearly basis, half yearly basis. Okay, so there time series is used. The difference between the two algorithms is linear regression is random. You get random, you take, let's say, a population, you take 15,000 records at random. Now that random sample may not contain the dates in a sequence. Okay, so generally in such cases, we avoid the date. But in case if you want to take a portion of the date, then whether the date is in a date time format or a string format, it doesn't make any difference. Because anyway, you are going to extract that portion and have it as a separate field and remove the date from the data set. Okay. So for example, if let's say I have something called order date. Okay, and this is in a string format. So the value could be 12/5/2019. And the next one could be 19/7/2020. Okay, now the year is of no use to me. What I want to find is what is the monthly pattern of sales. So here I will extract 5. So I'll create one entry called, let's say, month, which is going to be an integer. So this will translate to 5. This will translate to 7. And then I will remove this data from my data set. Clear? Who asked this question online? Is this clear to you?
Yeah.
Okay. Okay. So now that we are done with the basics, any questions, any doubts? Okay. So now we can start the linear regression. So what did you learn in linear regression? Tell me that.
The base fit line.
Okay. And
Using the X variables to predict the Y.
using the X to define Y. Okay. So what is okay, fine. So if I say that linear, so the objective of a linear regression is we want to find an equation where we predict what is the value of Y. Y is also known as the what variable? Dependent variable. Okay. So we want to find out the value, or we not find out, we want to predict the value of Y based on the list of features. Okay, features means what are the different factors that influence Y. Okay. So I'll give you a simple example and see where is linear regression, why is it important. Now let us say that I am considering the sales of a certain company. So let's take the last 5 years. This is 2016, 17, 18, 19, 20, and 21. Okay. Now the sale for 2016, let's say it was 50 crores, 51, 33, 39. Okay. So I'm just putting some random numbers. Now I want to find out what is the expected sale in 2022. What is my input data? The sales figures. Now, can I predict the value for 2022 given only this? Yes, no? No. If you have to guess what could be the approximate sales, then
yes. The 2020 is dependent on the all year. that time we predicted 2020.
So how will you guess what is the sales for this year?
If we have to guess, then we can see the general trend over the years, and then by taking some average.
Average. Okay. So if I take the average, good, we can take an average, isn't it? Because I don't have any other information. So let's say take an average of 50 plus 51 plus 33 plus 39 plus 47 plus 43 upon 1, 2, 3, 4, 5, 6, 43.8. So this is my prediction for 2022, a simple average of the last 6 years. Acceptable?
Yes.
Because nothing else is given to us. Okay. Now, what is the meaning of this number 43.8? So let us plot this. So here along the y-axis and along the x-axis, I have the different years. Now here the values range from minimum is 30 and maximum is 50. Okay. So here if I start at, let's say this is 30. And this is 50. Now, what is the prediction value? 43.8. So that means my predicted value will be somewhere here. Right? Approximate. Now, what are my other values? So these are the years. So for 2016, it is 50. So it is this value. Then 51, this is this value. Then 33, it is somewhere here. 39, so let's put this somewhere here. 47, so that will be somewhere here.
So it should be above that side.
40.
47 should be above that line, right?
Which line?
The mean line, because it's 43.
Oh yeah, okay. And this is how much? For 39, no? 47. This line should have come down actually a bit.
Yeah.
This is 39, 47. So this is 47 and then 43 somewhere here. Okay, some random data. Okay, so the red line is the predicted value. This is the predicted value. So can I say this is the best fit line for this model?
Yes.
It is a best fit line. But is this a good model or a bad model or not a good model?
Not a good one.
Okay, not a good model. Now, what are the errors in this data? What do you mean by errors? Errors are the difference between my expected value and the predicted value, isn't it? So this is the expected value. This is the predicted value. So this is the error for the first data. This is the error for the second data. This is the error for the third data. This is the error for the fourth one. This is the error for the fifth one. And this is the error for the sixth one. Okay, so the objective of a linear regression is to minimize the errors. It should have least errors. Now, if I simply calculate the errors, what do you think will be the numbers? What is the error? Sigma of E, which is actual data, which is represented as Y, subtracted by the predicted data, which we generally indicate as Y hat. So Y minus Y hat. So we can see here that if I calculate the error, now with 6 data points, it may not be very obvious. The positives and negatives, they cancel out each other. Okay, so we end up with sigma E equals 0. Okay, it may not be exactly 0. It's a value which is very close to 0. So what does sigma E equals 0 signify?
Error is minimized.
Correct. Error is, there is no error here, isn't it? So sigma E equals 0 means no errors. When I say there is no error in the data, in the prediction, what does it mean?
The line is best fitted for the or
No. That's a general meaning. But here, if I say there is no error, is that a true statement?
No.
No, because it is contradicting the figure that I have. There is a gap, there is an error, but I'm also saying error is 0, which is wrong. Okay, so how do I say that this model contains errors? So if you look at this value, this is, I just write the number, it is how much? 43.8. So I just put this 43.8. This is 50. This is 51. Then I have 33. This is 39. This is 47. And 43. Okay, now what is the error for the first one? Y minus Y hat. So 43.8 minus 50. So that will be around minus 5.2. The second one, minus 6.2. The third one, 9.2. Okay, this will be 4.2. And the next one will be 0.8. So if you sum up these errors, approximately it is going to be 0. Okay, but this is wrong information. So how do I ensure that I give the correct projection that we have errors in the data? So this is where we do the square of the errors. So when I square the errors, what do I get? Minus 5.2 becomes some 26 point something. Minus 6.2 becomes some 38 or something, 37, 38. 9.2 becomes a big number. 4.2 again becomes some 17, 18. Now, if I add all these numbers, I get the actual error in my model. I can either do square or I can take the modulus. Both are same. We generally take the square so that we can exaggerate how much is the error. Okay, so now if I write it, so this is y, this is y hat, 43.8. Fifty 51, 33, 39, 47, 43. Error y minus y hat. Okay, this is my error. So sum of error will be okay, it is approximately 0 because I have a very small data size. So how do I say that my error is large? I'll simply square this number. Okay, so I'll write this multiplied by this. Now, how much is my error? 240.84. Okay, so what this means is I have built a linear regression model where I have got a prediction and my training error, my error in the model is 240.84. Okay, so can I say this is good or not good? Now, I cannot say good or not good because I need to compare this with some other number. Okay, only if I do that comparison, I can say whether this model is good or not good. Okay, so this is model number 1. This is concept clear.
Yes.
So the objective, so here we'll just discuss a few things about what is linear regression. So first thing in a linear regression is to establish a relation between the y variable with the coefficient of the features. Okay, a lot of people say that it is a relation between y and x. It is not y and x, a linear relation. It is a linear relation of the y with the coefficient of x, which is this one. Is this clear? So this defines a linear regression equation. So this is what gets built when you build a model using the data. So when I have multiple features, I have B1, X1, B2, X2, etc. till Bn, Xn. Clear? Now, right now, I do not have any features in my data set. Okay, there is no X component. So that means the Y value is, what is A? The Y-intercept. So in this case, what is my Y-intercept? The mean value, which is how much? 43 point, whatever number I have, 43.8. Now. Clear? Now, if I do x1 square, I can modify my data as per my wish. If I take y equals x1 square, will I get a linear relationship? No, it will probably be a curve or a parabola. Okay, so y equals x1 square is not linear in nature. Or if I take a third degree polynomial, x1 cube, will this give me a line? No. If I have the coefficient a into x1 square, okay, it may not be linear because it is cutting down the power of x1 square. Let's say the value is minus 1.5. So it may be linear, I don't know. So that's why the relation is between y and the coefficient of x. Can the coefficient be squared? Can I have this?
Yes.
Of course, I can. Now, are they having a linear relationship?
Yes.
No. Because a1 square. Okay, a1 has to be a single number. I mean, not a polynomial. That's the difference. Okay. Online, any questions from anyone? Okay. So now we'll quickly discuss about the objectives of a linear regression. Number one, to build a model which will reduce the sum of squared errors. So this component of sigma E. So this is called sum of squared errors. Okay. Now, if I divide the sum of square errors by total number of entries, what do I get? Mean squared errors. Okay, I get MSE. And if I take a square root of MSE, what do I get? RMSE. So to evaluate a linear regression model, I can use any one of these measures. This, have you done this in the class?
Yes, sir. These terms.
This you know these terms. SSR, MSE, RMSE. Okay. So the objective is reduce the SSR, and number two is to not build, it is to draw the best fit line. And the best fit line will always pass through the centroid of the data. Centroid means midpoint of X and Y. Okay. So how many best fit lines can you have? You can have a lot of best fit line. This can be a 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 best fit line. So which is the best line? The best line is one which gives you the least SSR. Okay. Now in linear regression, we have two varieties. What are they? simple linear regression and multiple linear regression. What is a simple linear regression?
Single X variable.
Correct. Simple linear regression is one which will have only single feature with a single Y variable. What is a multiple linear regression?
Multiple X.
You have multiple features. So I'll have x1, x2 till xn, which is going to give you a Y. Now coming back to this example of sales. Does sale depend only on sales? Does the future sale prediction depend only on the past sales? No. It can depend on other features or other factors also. Okay. Now, how do I improve this model?
Adding features on which the sales they need them.
Okay. By identifying what are the different features which I think are important. Okay. Now, if I include one feature here, so let me take the same data. So right now I have the Y hat. Now, if I take one more feature, let us say the X1 is research amount, research and development. Okay, I do some market research and I am funded for that research. Okay, so for the first year, let's say the research, the budget allocated was 2 crores, assuming this is crores. For the next one, it is 2.4 crores. Here it is 4. For the next one, it is 4.2. Here it is 5. Here it is 7. Here it is 6. Let's assume these were the numbers. Okay. Now, given this information, can I say that this is going to be a good model?
No.
Why did you say no?
Because of only one feature and we add, there will be no result. There are multiple.
We're just considering one feature for now. We'll come to the other features later. Okay? These are all dummy numbers. Okay?
So we need to check that squared error with the previous mean error, and then if it is
good. Right now, I cannot say whether this model is good or not. I mean, I won't say good, better than the previous one. Okay, unless I know what is the value of the coefficients. Okay, once I know the values, then I will do the predictions. Then I will calculate the SSR. Then compare this SSR with the previous SSR. If the value reduces, it means this model is better than the previous model. If this number is more than 244, it means that this is not a good model. Clear? Online, any questions? Okay. So I'm just going to put some dummy numbers. You know how to use linear regression in Excel?
No.
Okay, I'm just going to try out with some dummy numbers. Okay, if this doesn't work, then I'll probably build one model in Excel and have the actual data. Okay, so let's, for the time being. So what happens in a linear regression? So linear regression builds one equation called the equation of the line. So y hat equals a plus bx, where n stands for the number of features. Okay, if we have 5 features, b1 x1, b2 x2, b3 x3, every feature will have its corresponding intercept coefficient. Okay. So right now we have only one single feature. So I'm going to create 2 values, one for A and one for B. So let us take the value for B as, I'm just guessing on some number. Let's assume it is 24.45. And for B, I'm going to take the value as 2.336. Okay, so I'm just taking some random numbers. So assume that the value of A is so much, B is so much. Now I want to make some predictions. So assume that for the next 3 years, the value for R&D, the amount is 10 lakhs, 13 lakhs, and 15 lakhs. Okay, this is the projected R&D amount for the next 3 years. So given this number, can you predict what is going to be the sales? This may not be a right number. Maybe I can increase this to 40.45. So I have done the calculations and I have come up with the value for the A, that is the y-intercept, which is 48.45, and the coefficient for R&D, which is 2.336. So with this information, can I now calculate or predict what is the value of expected sales for the next 3 years? What is it?
48.45 plus
A plus BX,
yes,
isn't it? So what is the value of A? 48.45 plus BX. So B is given to be this one. What is the value of X? 10. So the expected result is 71.81. when the value of the R&D amount is 13, then it is 78. If it is 15, it is 83. Okay. Now, what can you tell about the X variable? Can I say R&D causes high sales? Can I make this statement?
Those are just predicted values, right? As per the model, you make that statement.
I can make the statement, isn't it? Going by the general trend, more money you put into R&D, it is overall, it has given a positive sales. There could be fluctuations, no doubt. You will never find an all positive or all negative. There will be business cycles going up and down, but overall trend is positive. So here I'm saying, or I'm claiming that R&D causes sales. So this kind of a conclusion is called as a causal relationship. Causal. X causes Y. Or we can say Y is caused by X. So this is called a causal relation. Is this idea clear?
Yes.
Online, any questions? Okay. Now the next thing is, we have done the prediction. We have established that X causes Y. But what we have not done is whether this model is good or not good. Is this a good model?
Predicted because of the validation problem.
We have not validated it. Okay. So we need to validate this, or rather we should take the same A and B values and do the prediction on which one?
On the remaining data.
On the actual data.
Actually.
And then see if the errors are reducing.
Yeah.
Okay. So let's do this. So this is the actual data. This is the Y hat. Actually, this value should come here, because that is the predicted value, not the actual value. Okay. So now let's do the prediction. So we can just copy this formula from here to here. Okay, I'm taken dummy values, so it may not be very accurate. I'll just get the actual numbers. So these are predictions. So let's leave them aside. Now, what is the sum of squared errors?
Predicted minus actual.
Predicted minus actual. So y minus y hat. Y minus y hat. Okay, now this is dummy data, so it is not giving a very exact number. So ideally, we should calculate it. Okay, so I'll do that calculation and tell you, but the value should definitely be less because I have a dependent value. Okay. I have an independent value, so the errors should be less. So here I can say that this is definitely not a good model because one of the errors itself is more than the sum of squared errors. Okay, so ideally this number should be around, let's say 38 or something. This could be around 1.06 or something. Yeah, now this looks, yeah, this is better. Now, if I calculate what is the SSR, so sum of even this is on the higher side, so maybe let's think. Okay, I'll just calculate it and find out. Okay. So ideally, this number should be less than 244, which is this one. I'll calculate it and tell you the coefficients. So this is how the evaluation has to be done. So if the error is less, so right now because of random values, I'm getting a high error, which indicates this is a bad model. But now if we do the proper calculation, you will see that this number should be way less than 240. Okay, because profits are, sorry, not profit, sales does not depend only on the previous sales. Sales also has other factors. And one such factor is the R&D amount. Okay, so I'll do that calculation and let you the exact value. Then you can figure out how the difference is there in the errors. Okay, we'll take a small break. It's 11 o'clock, 11:15 we'll come back. Okay, let us start. So I found out the values of A and B. It is 47.6 and minus 0.883. Okay, those are the values. Again, not random numbers. In Excel, you can do a quick calculation for regression. Okay. So from there, I found out. So now if I apply the values for A as 47.6 and B as 0.883, now the predictions are 50 predicted as 45.8, 51 predicted as 45.5, 33 predicted as 44, 39 predicted as 43, 47 predicted as 41, and 43 predicted as 42.3. So in the morning, I asked you, when I do the prediction on the same data, will it be 100% accurate? Is it 100% accurate? No. So what are the errors? These are the errors. Now, if I calculate the SSR, so that is going to be sum of $226. What was the previous error? 240.8. So now tell me which model is better. Okay, so whenever you are reducing the error, the model which has the least error is the best model. But can I conclude that this is the best model? No. No, this is better than the previous one, but this is not the best. So how do I ensure that I build the best model?
The error should reach its minimum value.
The error should be minimum, yes. Yes, and
research.
Research
Modification.
as in
Modification in value in our basic in data.
How can you modify the data? You cannot tamper values. Yes, people online. How can I build a model where I can reduce the errors further? It is by adding new features. Okay. So does sale depend only on R&D? Can sales depend on other factors also apart from R&D?
Yes.
It can. Okay. For example, if I have features like let's say I have features like employee count or employee number of employees, then production cost, for example, then let's say tax component,
Transportation.
okay, whatever it is, okay, transportation. Okay. So I have all these features which may contribute to sales. So because I have all these different features, can I now say that R&D causes sales, which we did in the previous example? Now, can I have a causal relationship here? Can I say R&D causes sales when I have the other factors?
Yes, this is considered that time the SSR will be reduced.
So depending upon the coefficient, we can tell which factor is affecting how much, which feature is affecting how much.
Okay. Now, in this example, the second example, I do not know what is my SSR. I'm only giving some examples of factors that could play a role in predicting the sales. Okay. Now, is employee necessarily be an important feature? Does the production cost necessarily be an important feature to predict sales? Does transportation necessarily be an important feature to predict sales? Okay, I do not know. Unless I have that in my data, then do the analysis and find out what is the coefficient. Okay, so you probably would have done this in the class, the concept called feature selection. Have you done this? Yes or no?
Yes.
What do you mean by the term feature selection?
We are selecting only those features which are really contributing towards the change in Y.
Correct. So feature selection means take only the important features that affect the Y variable. Okay, other factors, even if it is there in the data set, it may not contribute and it can also result in errors. I won't say errors, it will result in overfitting. Error is not the right word. For example, if I take, if I have to predict the temperature of a place. Okay, let's say Pune. Now, can I have a feature average weight of male and average weight of female in my data set? Okay, there are other factors also. I'm having two more features, average weight of men and average weight of women. So do these factors, do these features play any role in predicting the temperature of Pune? Okay, it may sound very funny, ridiculous, but you do not know. Unless I have these features, do the prediction and study the coefficients. Okay, at a broad level, it may sound that it doesn't make any sense because weight has nothing to do with prediction. Okay, but if you, if a new research says that weight can cause, it could be an effect in some way, the temperature of a place, then this becomes an important feature. Okay, just a thought. Based on the weight, your weight, can you decide the vehicle?
Yes.
Yes. Can vehicle cause change in temperature?
Yes. Pollution.
Okay, it can. Okay, that is why I said At a surface level, this may look very funny. Okay, what has weight got to do? But if you probe into that feature, does it have any link? Does weight has any relation with the choice of car? Does choice of car has any relation with the pollution? And which in turn will affect the temperature. So then you will realize that this has some importance, which may not be very significant, but maybe it is slightly significant. Okay, so unless and until you build the data, build your model, and then do the prediction, then analyze the summary. So till that point, you should not judge whether it is a good feature or a bad feature. Some features are very obvious, it should not be there. Okay, for example, chassis number of a vehicle. Does it have any relation with temperature? It is an obvious no. Okay, what does your salary got to do with temperature? Okay, so there is no immediate or direct relation between these two. Okay, so this is called as feature selection. So select the important features. So how many features should be there in your data set? Again, there is no count. You should ideally have at least one feature. But at the same time, you should also not have too many features. Okay, so this is a classic, there's a term for this. This is called curse of dimensionality. Have you heard this term in your class? Curse of dimensionality. So on one side, we are saying you should have features. And on the other side, we are saying you should not have features. Okay. So what is the ideal? Is there any industry standard you should have a fixed features? No. That is why we always say your data or your model should contain the best features. The best features could be 1, the best features could be 10. Select the best. Okay. Now, there are other terms which are related to linear regression. One is SSR. The other is SSE and then SST. Okay, sum of squared errors, SSR. Total sum of squared errors. Sorry, SSE is sum of squared errors. SSR is sum of squared errors due to regression. And SST is total sum of square errors. So SSR plus SST equals SSE equals SST. Have you heard this term R square?
Yes. Yes.
What is R square?
SSR divided by SST.
SSR by SST. Okay.
SST.
SST, correct. But what is R square?
It explains how much your features are showing the variability in the dependent variable.
Correct. How much variation you have in the features to explain the Y. So what is the concept of R square? Should this be a high value or should this be a small value?
It should be high.
It should be high. Now, does a high value necessarily mean a good model? What is the range of R square?
0 to 1.
0 to 1. Because it is a square, so it cannot be negative. Okay, so it is 0 to 1. If I have an R square of my model, which is giving me a number let's say 1. Is this a good model or a bad model?
It's a perfect model.
It's a perfect model. So should I take this model for my predictions? Yes or no? If R square is 1.
Yes, you can use it.
Online, if I'm getting an R square of 1, should this model be considered or should this be discarded?
Depends upon the number of features that are added to predict the line. I mean,
Okay.
if
Think
the
of whatever
variance
number of features I have. Let's say I have 4 features. And I'm getting an R square value of 1.
So are the features really causing any change in the variation? So that factor is also important.
Correct. Okay, so when I'm getting an R square 1, this is a perfect model. So when you have a perfect model, it means that it is wrong. Now, why is it wrong? Now, assume that the data that is coming in for testing or for prediction, there is a change in the data. Okay, the format changes or the way you have formatted the data, that changes. Will the model be able to predict? No, in that case, it will be a severe case of overfitting. Okay, model will generalize in that case. What I have seen there, but it does not know that this is a transformed data. So in that case, it will give you a very poor result. Okay, so R square is 1 is a very bad model. So that's why we say R square should be high. But we never give a range that it should be crossing this number or it should be between this. Can never have. Even if I have an R square of 0.45, okay, this is considered to be a good score, okay, provided I have the best features. So I can have 2 best features out of 10. But because of limited features, R square can show a small number, but that is considered to be good. Okay, so we'll discuss about R square in a while. So what are the 3 values that we have? So if I draw a line to indicate the errors, so this is the prediction. So we have Y. What is Y hat? The predicted value. Okay. What is this line?
Mean.
The mean. Okay. So this is Y bar. Okay. And then we have one more line. Let's draw this. What is this?
Why?
Sorry, I put the Y hat in the wrong place. This is the predicted line, isn't it? So we have Y hat, which is the predicted line, best fit line. We have the mean value, which is this, and then we have our data. Okay, now we have 3 terms. The difference between the data and the predicted value, which is Y minus Y hat. Then we have the difference between the predicted value and the mean value. So we have Y hat minus Then we have so y minus y hat. That is called SSE. So I put the square here. Y hat minus y is called SSR because that is the error due to regression. So I put the square here. So summation of these two is the SST. So R square is a fraction of the sum of square due to regression divided by the SST. So how much is the variation in the mean divided by how much is the variation in the regression, in the total errors? Okay, it is a variation between the mean and the values of regression. So the fraction is called R square. So greater the number, better is the model, general perception. Okay. So when I include more features, when I put more features, what happens to R square? R square will increase. Okay, R square increases. So can I say my model is becoming better and better when I'm adding more features?
No, not necessarily.
Not necessary. Okay, the same thing that we discussed some time back. More features will increase the value of R square. But does it mean that I'm building a better model? Or I'm building a model where all these features that I have added are significant? Answer is need not be. So how do I determine whether my model with these features are significant or not? So that is where we have to use another measure called adjusted R square. So adjusted R square is an unbiased valuation of the features. So when you add a feature, it is going to first find out whether it is significant with respect to the Y. If there is any link, it will increase its coefficient. If it is not significant, the adjusted R square will be lesser than the R square value. It will decrease that number. So we should always look at the adjusted R square value to find out whether your model is significant or not significant. Both these values will be shown. If you have seen since you have already done the initial linear regression, you'll probably recall when I do the summary of a model, I have two numbers, R square and AR square or adjusted R square. So adjusted R square will always be lesser than R square. So you should always consider adjusted R square to determine the model goodness of it. Is this clear to everyone, online people?
So revise the adjusted R square. Revise it.
Okay. R square shows the variation. Okay, so X and Y, what is the variation explained by the features? Okay, whatever is remaining is considered to be errors. Now, when I get a very high number, let's say 0.92, it means that 92% variation is explained by these features. Okay, does that necessarily mean that all these features are good? The answer is it need not be. Okay, so to counter this unnecessary increase in number of R square, we have another unbiased feature or measure, I should say, which is called adjusted R square. Okay, so let us say that I have 5 features, x1 to x5, which gives an R square of 92. So when I add the next feature x6, so what adjusted R square will do, it will first check whether x6 has any relation with y. Is it significant? So based on its significance value, it will either increase this number or decrease this number. So that number is called adjusted R square.
The x6 value is correlated with the y. That time what will happen?
Nothing will happen. It should be correlated, no?
Values will increase.
Yeah, if it is significant, it will increase. That's what I'm saying. If it is significant to explain why, it will have a value greater than this. If it is not that significant, then it will be less than this. So you'll probably have, let's assume this is not significant. So the value of adjusted R square will be something around 0.912 after adding x6. So now you have to analyze and then find out why there is a reduction in the R square, the adjusted R square, and then you can get rid of that particular feature. Clear? And again, formula and all that, you don't have to really worry about the formula, but in case if you want, adjusted R square is 1 minus. No, adjusted R square. It is 1 minus R square multiplied by n minus 1 divided by n minus k minus 1. So R square value is the value, n minus 1, n is the total number of, that is the sample size, and k is the total number of features. Okay, any questions so far? Now we'll come to the next section. I'm sure you must have done this also in the class, assumptions. What are the assumptions of linear regression? Have you done this?
Yes.
Do you recollect doing this particular topic?
Yes.
There should be a relation between the independent and dependent variable.
Okay, so first of all, assumptions are of two types. What are they? One is related to the data. And the other is related to the errors. Now, what are the assumptions with respect to data? X and what you said just now, X and Y
Should have a linear value.
should have a okay. So X and coefficient of Y, Y and coefficient of X. Okay, not X and Y. So coefficient of X and Y has a linear relation. Okay. Next.
There should not be autocorrection from the residual.
Okay, that is errors. So let's talk of the errors later.
Error shouldn't be normal distribution.
Errors again, we'll talk. Data. What is with respect to data?
Only 4 others.
What are we? The second assumption is, yes, online people, if you recollect any assumptions.
The sample of data that we are taking, it should be similar to the population data.
But how do you verify that? Do you have access to the population?
No, but there are some measures in statistics so as to measure whether the sample is the true sample of the population.
So the data should be normally distributed. Okay, this is the next assumption. Data has a normal distribution. Next. Data should not have outliers. How do you check for outliers?
The points which are above 3 standard deviation.
So how do you check outliers in your box plots? Okay, simple. Now, when you are plotting box plots for checking outliers, and let's assume that you have found out of 5 numeric features, 2 features have outliers. So what kind of outliers are they? Are they statistical outliers? Or are they the domain outliers? Domain outliers means for that given data, is that an outlier? Let's say the domain is engineering or manufacturing. So is that related to manufacturing outlier, or is that coming from the statistics formula and then it is classified as an outlier? So how do you determine that?
It should be domain outlier.
No, what you get is a statistical outlier. Okay. Now, what is the difference? What is a statistical outlier? Now, if you plot the data, the first vertical line is quartile 1. Okay. What is the second vertical line? Q2 or the median. Q3. Okay. Now, how is the outlier determined? Based on the value of left whisker and right whisker. I think last time we discussed this, isn't it? No. So this is the left whisker and this is the right whisker. Whiskers mean they are the extreme values, which is not an outlier. Anything beyond that is an outlier. Okay? So if I see 1 point here, or 2 points or 3 points, these are statistical outliers because they come from the formula outliers to the right equals quartile 3 plus 1.5 times IQR. Okay, this is the standard formula. So it is a statistical outlier. But does that necessarily mean this is an outlier for the given domain? It need not be, once again. So how do I suppress this value from appearing in the box plot? I don't want to give a wrong meaning to the box plot. Because if I have to do a presentation to the experts and everyone knows there cannot be outliers. And if I show them there are outliers, it is wrong. Okay, so I want to suppress them. So how do I ensure that these points don't appear in my graph?
We can normalize the data.
Even then it will come. Because outlier is an outlier, whether you normalize it or not.
We can extend the values. Instead of 1.5, we can change it to 2.
Correct. Okay, this 1.5 is a statistically significant number. Okay, which can be customized. So if I increase this to, let's say, 3 or let's say 3.5. So what is going to happen to the whisker? What is going to happen to the right whisker?
It will extend.
It will extend to the right. Okay. So this line, vertical line, will come here. Okay. Now this number won't be now shown as an outlier. So this will now stretch. Now anything beyond this is an outlier. Now this has fallen into the acceptable range. Okay. So the assumption of linear regression is there are no outliers. So when you are dealing with outliers, you have to be very careful. Not every outlier that you get on the screen is necessarily an extreme number. Okay, next. The next assumption is when we talk of features, what is the other name for the features? Independent variables. Okay. Now, why are they called independent variables?
They should not depend on each other.
Correct. Here in the first point, we said X and Y should be dependent. Okay. Now, the other assumption is X and X should not have any dependency. So, X and X, no dependencies. So when you have a dependency between X and X, that leads to a problem called yes, anyone? It is called multi-collinearity. Multicollinearity is when features are dependent on each other. So let's say that I have the y here, then I have x1, I have x2, I have x3, I have x4, I have x5, I have x6. I have, let's say, 6 features. Okay, so y should be related to x, that is coefficient. But if I have a relation, let's say x1 is related to x4. Okay, this should not happen. How do I know x1 is related to x4? How do I find that out?
Correlation.
Correlation. Okay, we have done that in the class. Correlation between two variables. So the correlation between x1 and x4, if you have a significantly high or low number, that is high positive and high negative. So let's say if the value is minus 0.9, or if it is having a value of plus 0.88. So they are significant, highly negative or highly positive. So what should you do in this case? If you see correlation between features,
Remove one.
you have to remove one. Anything else that you can do? Now the question is, if I have to remove one, which one should I remove?
Similar value.
Yes, that is one way. You can find similar values and remove that. But similar values, it is there's another
Error closely related.
errors.
Closely related to the value, they can be removed.
How do you do that?
Suppose 0.9 and 0.9 and 0.97 value. Error is selected only one value, they can be good represented.
What is 0.97? Correlation between?
Value. Suppose 0.9 and 0.98 and 0.
Now, what are these values? 0.97. Correlation values between x1 and x2.
Yes.
Okay, one second. Let me just write it. So 0.98. Okay.
And another value is 0.99.
What is that other value? You can have only one value, isn't it? The correlation.
X4 value.
No, how can x1 have 0.98?
I think he's trying to say we can remove one variable which is less significant as compared to one else.
That is one way of looking at it. But for that, you need to do the summary of the model and then find it. Oh, hypothesis testing. That's a part of hypothesis testing. Okay, that is, we'll come to that later on. But based on these numbers, no, you cannot have two values, isn't it? One for x1 and one for x4. Correlation is for two features, one number. So which one will I remove? X1 should be removed or x4 should be removed? Again, there is no straight answer to it. If I want, I can remove x1 and I can retain x4. Then you build your model, check for errors and see how much is the error. Then build one more model. In this, you retain x1 and remove x4. Then you build the model, check for errors, see the difference between the two, which is giving less errors, you take that. This is one way of looking at it. So there are some people also take x1 and compare the correlation with y. Then take x4 and compare the correlation with y. Okay.
Simple relation.
Correlation,
Okay.
x1 and y.
Yes.
Both are numbers, isn't it? So if X1 and Y, it shows a high correlation, take this. If X4 is showing a higher correlation value, take this. Okay, these are some standard methods people use. Of course, you are free to use any method. That is up to you. So one way is removing this, use this technique. Other technique is if X1 is related to X4, I can do something called feature engineering. That means I can combine X1 and X4 and make it into a single variable. Okay, use any formula that you think is relevant. Let's say X1 plus X4 or X1 multiplied by X4. Okay, whatever formula is relevant, use that so that I get the value of X1 also, I get the value of X4 also. So once I create a new feature X1, X4, now what is the next thing you should do? Remove this and remove this. Okay, so out of 6 features, you have added 1, that becomes 7, and then remove 2. So your total dimension now reduces to 5. So this is one way of preventing overfitting by reducing multicollinearity and at the same time also doing feature selection.
So I have one doubt. So what is the actual impact of multicollinearity on the model? Suppose we have 2 variables which are multicollinear. How it will affect the model?
It will be overfit. You will have severe overfitting. The errors will be high. The R-square will be high. And you will do a wrong interpretation. Now, there are cases where you require both the variables, even though it is showing multicollinearity. Okay, one value has to exist with the other. There are domains. For example, marketing, if you look at, let's say, sales done in different regions. Okay, North will have some relation with, let's say, West. Okay, East will have some relation with Northeast, for example. So I cannot say that because there is a correlation, remove one. Okay, so you need to think of ideas how I can get that information also. But at the same time, there is no correlation between features. So you can use these techniques, feature engineering, you can sum them up, or you can take an average, or you can take a median value so that I get that number. Okay, clear? Can you have a correlation for categorical data?
Yes. Yes.
सोच के बोलो.
नहीं sir. We can include the categorical variables in the model. So we might have correlation with the
How? Dependent नहीं. Correlation among वही मैं पूछ रहा हूँ. Can you have a correlation? It doesn't make sense. Okay, so correlation has to be done only for numeric data. So this is part of the EDA. When you are reading the data, what are the EDA that you need to perform? The EDA is not a standard procedure that is applicable to all types of data. Number data will have a specific set of EDA. Categorical will have some things will be common. For example, null check is common. But checking for 0 is not applicable to categorical in all cases. Okay, correlation is not applicable to categorical. Checking for spaces is not applicable to numeric data. Number of levels is not applicable to numeric data. So when we come to the EDA, we'll discuss that part. Okay, so the assumption is when you have multicollinearity, you have to remove the multicollinearity. Otherwise, your data will be, your model will have overfitting. और क्या है assumptions? The number of rows, that is the total number of observation, should be more than the number of features. Ninety-nine percent of the time, you will have rows greater than columns. There could be exceptions where, for example, you're reading data of a face, facial recognition, facial data. Okay, so where the number of features of just the face itself will be some 100 to 150, but you may not have so many data points. So in that case, columns will be more than the total number of records. Then it becomes very difficult for you to make the regression analysis. Okay, so these are assumptions with respect to data. Now we'll come to with respect to errors. So first assumption is the mean error is 0. When I say mean error is 0, it means that I'm talking of the training errors. The next one, the errors have a normal distribution. The third assumption is the errors have a constant variance. What is the term used for constant variance for errors? Sorry? Constant variance with respect to errors. If you have done the linear regression, then you should have been aware of this term. Some online. ज़्यादा झाड़ू सबको.
आज ही online है कि? Online students, Utkarsha this side. Why you guys are attending the sessions online today?
Ma'am, actually my health is not good, so.
Okay. Aniket, he attends. Mrinal, what about you?
Yes, Utkarsha, I'm also not feeling well, so I'm doing well.
You're not feeling well?
Yeah.
Okay. Rest. I think only Chintamani attends online. Rest all will come offline.
My office is also going on.
What is it?
Office working. Like today is my office.
Office.
Okay. Baki time aata hai na sir? Can I speak to them for 5 minutes?
Okay, we'll just take a pause and Prasha will have the session.
This volume is low क्या?
नहीं हाई में है वो एक्चुअली थोड़ा ambient noise भी है. Disconnected to the mobile. Hotspot पे चल.
5 minutes.
Should I go out?
Whatever is preferable. Just feedback पूछना है मुझे उनको. Online students, am I audible to you?
Yes.
Yes, sir.
Guys, how is the session going? तो डर जाएंगे सर वो आपसे डर जाएंगे फिर बोलेंगे नहीं कुछ करेक्ट
Session is good with Prasha. We are understanding the basic concepts.
Okay. What is
which we were
covered
not
in
able
the
to.
session? Okay.
Sorry.
What was covered in last couple of sessions?
Yeah, basics were cleared, like for the stats and the SQL, whatever the mispoints were there, sir was clearing that.
Okay.
And now
linear
we start. Yes, linear regression we started today with now like basics has been done. Like we have started with like why we are doing it, why it is necessary to do this, what are the assumptions going on for that. Like
okay.
Basics are getting covered right now. So like when we go further, we can like think in a different way also.
Great. What about you guys? Understanding?
Yes, we are understanding. I just feel we should increase the pace because we are already behind so much.
Behind. So basic idea मैंने आपको दिया था ना कि 4.5 months already इनका semester 1 ही चल रहा है.
Already finished linear and logistic. That is what they said.
Linear and logistic is finished. It was linear was started, and during that itself, these people came up to me. There were 3-4 students who batch transferred probably. तो वो लोग को उन्होंने बोला कि नहीं समझ में आ रहा है. Semester 1 में कुछ भी समझ में नहीं आया उनको. Linear start हुआ था already उनके इसमें. But वो भी उनको नहीं समझ because Python ही clear नहीं.
That is what I was asking. A couple of questions which I felt should have been covered. So, lot of gaps. इसीलिए थोड़ा slow जाता है. I can finish this in 1 hour also.
But then again, we'll be on the same thing. We will work on it to minimize the duration probably. मतलब जो आप लोगों का duration month wise है.
Linear regression, logistic regression, वो base. Everything evolves from these two. Okay?
Correct.
Support vector machines, you have to understand logistic.
तो ये basic जब तक clear नहीं होगा फिर आगे बढ़ के वो speed up करके भी फायदा नहीं.
So that is why I keep asking questions. ये पता है ये क्या है? So I was not getting the response, so I see the gap with क्यों नहीं किया है.
Basic नहीं होता logistic नहीं किया था. Sir के कहते basic जो concept है ना R पर direct implementation है R कैसे निकालते हैं उसको formula देते हैं उसको कोई basic नहीं पता तो हम क्या करें.
Correct. Okay. तो अभी आपका SQL सबका तो clear है, right? क्लियर है मैं वापस एग्जामिनेशन रखने वाली हूँ सबका. ठीक है. फ्रॉम एसक्यूएल पाइथन एंड स्टैटिस्टिक्स तीनों भी एग्जामिनेशन आपके वापस होंगे. असेसमेंट नहीं होंगे, मेन एग्जामिनेशन वापस होंगे so that it does not affecting your scores. And once the exams are done, we will be going forward with your mocks semester 1 का. ठीक है. तो प्रिपरेशन स्टार्ट कर दो. नेक्स्ट वीकेंड से I'll be sharing across your exam papers. वो टेबल जो है टाइम टेबल that I'll be sharing on Wednesday, but this is a information probably कि आप लोगों का ये सारा चीजें कंप्लीट होने वाला है वापस. तो अगर उसके बीच में examination each day one examination would be there and then so that we'll be able to complete everything. and फिर mocks भी आपका pending है semester 1 का. so start your preparation. mocks का भी preparation start कर लो so that अगर उसमें कुछ issues है सर को सेशन में पूछ लो कि ये नहीं समझ में आया है. LMS में जितना कंटेंट अवेलेबल है इन क्लास एक्सरसाइजेस प्रोजेक्ट्स वो सारा सॉल्व करो घर पे जाके. अगर उस पे नहीं समझ में आ रहा है वो भी क्वेरीज रेज करो so that everything is clarified before the mocks. ठीक है. उसमें फिर गैप नहीं होना चाहिए. ठीक है. ओके सर इनकी जो असेसमेंट्स है जैसे अभी लीनियर होने के बाद असेसमेंट रहेगा इन क्लास तो यूजुअली हम लोग पहले वाले बैचेस को बोलते थे कि यहाँ पे आके कंप्लीट करो, मॉनिटर हम लोग करते थे और कंप्लीट, लाइक काजल यूज्ड टू मॉनिटर एंड शी यूज्ड टू गेट इट कंप्लीटेड. बट नाउ दैट इट इज क्रिएटिंग अ लॉट ऑफ गैप एज वेल, बिकॉज वो लोग को पेपर डिस्कशन सेशंस भी नहीं मिलते हैं, specifically weekend वाले बैचेस को. तो we'll complete it into the session only. Let them cover it up within the 2 hours. 4 hours का सेशन है, 2 घंटे ये लोग यहाँ पे कंप्लीट कर लेंगे और लास्ट के 2 घंटे फिर उनको अगर कोई क्वेश्चन नहीं समझ में आया है तो वहाँ वो आप सॉल्व करके दे दो. नॉट ऑल द 10-15 क्वेश्चंस, जो सिर्फ ये लोग को मेजरली नहीं समझ में आया वो क्वेश्चंस को हम लोग पिकअप करके या ये लोग के लिए प्रैक्टिस करवा देंगे. सो लीनियर जब खत्म हो जाएगा आप मुझे बता दो, फिर मैं पेपर ट्रिगर कर दूंगी ये लोग को. तो फॉर ऑल द next Sunday.
So Saturday we will do 4 घंटे में, hopefully we can finish the hands-on. Sunday they can take it.
ठीक है. So this is how we'll be moving forward. ठीक है. Online students, please make sure that you all are coming to classroom. It is very difficult कि आप लोग online कर रहे हो और मुझे नहीं लगता इतना अच्छे से समझ में भी आ रहा होगा आप उन लोगों को भी. And then whatever they are raising concerns, बिकॉज हर बारी वो बोलेंगे उसके बाद फिर टाइप करेंगे चैट बॉक्स में. ठीक है. एनी क्वेश्चंस, क्वेरीज यू ऑल हैव, यू कैन रीच आउट टू मी. ओके, थैंक यू सो मच. थैंक यू सो मच.
Okay, so errors have a constant variance. There is a, okay, I'll tell you the name. The name of that is called homoscedasticity. Homoscedasticity means when I'm plotting the errors of the training data, it should be spread evenly. Evenly as an exact name, there should not be a lot of variation. If there is a variation, it means that my data, my model is not good. So that condition is called heteroscedasticity. So when will you encounter these problems? When you plot your model, when you summarize your model, and when you plot the model's results. Okay, here plotting se hi dikhega. There is no other way to see it. And of course, you can use there are some tests, hypothesis testing. There are some standard tests. Okay, but first point you have to do is, the first thing you will do is plot it and see. Sometimes plots are not very easy to understand. So in that case, you can go with the inbuilt tests. Now, what is homo and heteroscedasticity? ये वाला करवाया था क्लास पे when you were doing linear regression? Right. So let's say that this is my distribution of errors. Okay, so I have 0 error here. Then I have positive errors on the top and I have negative errors. Errors can be both positive and negative. We have seen in the class. Okay. Now, depending upon how many observations I have in my testing, in my training set, if I plot the errors, the distribution could be something like this. Okay. Each point represents one record. Okay. Now here, if you see that the errors they don't have too much of variation. Okay. Fluctuations. So this, I can call this as homoscedastic. Okay. Now, what you have to do is, when you plot this graph, you have to see the degree of heteroscedasticity. Kitna hai? How much is the variance? Do I have a lot of variation, or is the variation sufficient enough for me to do the prediction, or is it bad? Okay. So this is a homoscedastic data. Now you will get a graph like this along with one more indicator in the graph. And that is a line that goes something like this. Okay, so this green line, this should be parallel to the x-axis. That indicates homoscedasticity. So jitna variation rahega, the more the variation, more will be the curve. So your objective is to find out how much is the degree of variation based on this graph. Okay, now if I look at this graph, assume I get a green line like this. I can conclude this is homoscedastic. I can live with so much variation, no problem. But if I have, let's say, this is the 0, this is plus, and this is minus, and I have the error something like this. Maybe I can just put . Now, what do you think this graph is showing?
Not constant.
This is non-constant. This is a clear case of heteroscedasticity. So if you look at the graph of this, you will probably see the line something like this. It will be maybe something like this. Okay, so this shows the variation. See the difference between the two lines.
Parallel, the first one is parallel.
The first one is having less variation. It will never be an exact straight line. Okay? Don't assume it will be, when I said parallel just for a reference sake. So more straight the line is, or you can say less curvy, it is homoscedastic. The more curvy or the more arc you have, it means you have a heteroscedasticity in your model. Now, why does heteroscedasticity happen in the data? That is what you have to investigate. So the answer is multicollinearity. So you are asking, you know, what can happen if I have multicollinearity? This is one of the things that will happen. Okay, so always check multicollinearity. If you have multicollinearity, remove it. Even after you remove multicollinearity, can I have homoscedasticity, heteroscedasticity? Answer is yes. Okay, now how do I remove heteroscedasticity in the data? Sorry, from the model, not data. So to remove or fix heteroscedasticity, again, there is no guarantee that after applying these techniques, heteroscedasticity will vanish. Okay, because you cannot tamper data you cannot keep normalizing and standardizing as per your wish. Okay, because you have to keep track of what you're doing. Okay, so it will not completely be removed. You have to analyze and find out to what degree you can take the heteroscedasticity. Okay, so there has to be some element of errors that you have to accept, known risks. Okay, so what are the different techniques that I can use to fix heteroscedasticity? Number one, you can standardize the data. Okay, before that, I'll just fix heteroscedasticity. I can fix it in two ways. I can fix my X and I can fix the Y. Either you fix the data or you fix the Y variable, but not both. Don't fix both at the same time. So,
why is that?
Because when you do the final prediction, you have to reconvert everything. Because to fix this problem, you're converting the data. That is, you're transforming the data into a different form. Then you're also transforming the Y into a different form. And then you get a result. So when you get the result, you have to retransform everything back into its original form. So it is not required that you have to transform both. Any one is sufficient. But that does not mean that you should not do. You can try it out. Okay? You can try it out, no issues. But again, when you're trying to find the errors, you have to be careful. Because you have to match the errors of transformed with errors of transformed. A lot of people do this. For example, they have the Y variable. Let's say it is 10. Then they transform the Y and it becomes, let's say, 1.3. Okay, after transformation. Now, when I predict it, in what form will I get the prediction? Y or transform Y? If I do the prediction. In the transformed Y, because this is now my Y variable. So let's say that the value that I get after prediction is 2.5. So how much is my error? Is this minus this or this minus this? First one or second one? First one. A lot of people do the reverse. They do the actual Y minus predicted Y, which is 10 minus 2.5, and they get a big error. So you have to be very careful when you are making these kind of transformations. It can get very sensitive if you don't pay attention to the details. So what are the different ways to transform the data? So let's take the value of X, that is the features. Have you done any kind of transformation? EDMA, Python? Statistics, you must have at least done the theory part, transformation techniques.
You mean data transformation into the normalized form, or yes?
Yeah, no, you must have done this. What is the technique called? Z-score transformation?
Yes.
What does Z-score transformation do? Transform the data between -3 to +3. Okay, this is one way of transforming your data. Then you have a min-max technique. Min-max technique will transform your data between 0 to 1. Okay. So for example, I have a number called, let's say, sales. And the values are something like this: 37, 60, 49, 43, 65, 59. Okay, let's assume that these are my numbers. Now, when I transform this gets transformed into a range. This is transformed sales. 37 gets converted into a number between 0 and 1. Okay. Now, how does this happen? So the formula for the transformation is min-max is the value, the actual value, x minus minimum of x divided by maximum minus minimum. So here, what is the minimum x value? 37. So 37. Then max minus min. What is the maximum value here? 65. 65 minus 37. Okay, now what is the value of x here? X value is the individual values. So for the first one, it is going to be 37 minus 37 upon 28. So this becomes 0. Then I have 60 minus 37 divided by, sorry, made a mistake somewhere.
Formula is fine.
X 60 minus
37.
27, correct. Okay. So 27 upon 28. So this will be around 0.9. This will be around 0. Let's say 72. This will be around 0.71. This will be around 0.8 and this will be around 0.5. Okay, I'm just putting some numbers. So after transformation, the value gets converted to a range between 0 and 1. You can use this technique also. What are the other techniques that you are familiar with? Online? Yes, statistics, where you should have done this. When you have a data which is not normally distributed, steps taken to convert skew into normal. You can do log transformation. And now I can take the data and take a log of it. Let's say value is 30, log of 30. I can take natural log, I can take base of 2, I can take a base of 10, I can take any base value. So you will get the value.
For the first two transformations, the distribution after the transformation will be same just as it was before, right?
Transformation?
Yes.
Or sorry, a distribution.
Distribution of the values.
And
in the log transformation, we can convert from skew to normal.
See, 99% of the data will never have normal distribution. Okay, so that assumption of linear regression that data is normally distributed may not hold good every time. There will be skewness. Okay, so you have to live with the errors. So your objective is try to minimize the errors. So how do you minimize? You have to do these. See, everything is interconnected. You have errors because of this. Because of that, you have heteroscedasticity. Okay, so everything is interconnected. So you cannot look at only one particular problem and try to identify that. It's all linked. So log transformation, I can do base 2, base 10, base 5, base 2.5, whatever you think of, natural log 2.71. Then I can do inverse transformation. I can do square root transformation. These are some standard methods. Okay. And whatever transformation that you can think of, you can put in your own logic and come up with those values. So if this is done, y will remain as it is. Okay. But if you decide, to transform y, then x will remain as it is. So when you decide to transform y, this is called box transformation. Box-Cox transformation means that I am taking the y value and I am raising the y value to a lambda. Lambda is generally a very small number. Let's say 0. Let's say lambda is 0.21. So 30, if this is the value of y, so 30 will be raised to 0.21. So you will probably end up with a number something like this, 1.586 or something. Okay, I'm just putting some dummy number. So you're transforming the y from its original form to a number raised to some lambda such that y becomes normal distribution. Clear? So in this case, we have, of course, we have functions to do the transformation. You don't have to worry about the formula and all. So the only thing that you have to know is what is the lambda value and what is the transformed y. Okay. So once you get the predicted value, so what is the predicted value going to be? In which form will it be? In the same form. Now you have to convert this converted form into its original form. So for that you need the lambda. Okay, so I'll give you the formula later on when we do the hands-on and if we have to do this exercise. Okay. So then we convert this back into its original form. So these are the two ways in which you can minimize the impact of heteroscedasticity in your data. Any questions from anyone online? Aniket, Ankita, Chintamani, Kamlesh, Keshav, Mrinal, Yash. Okay. Now, sometimes to check the heteroscedasticity, the graphs may not always give you the correct picture. So you may have to do some tests. So one such test is called NCV test, non-constant variance test. non-constant variance test to test the heteroscedasticity. There is another test called the Brosh-Pagan test. Sometimes called BP test. So you have White's test, you have lots of other tests, but we'll stick to these two. So here the null hypothesis states that my model is homoscedastic. And the alternate hypothesis is it is heteroscedastic. Now, can you tell me, based on the alpha value, what alpha value will tell the model is homoscedastic? What alpha value will tell this is heteroscedastic?
P value greater than alpha that we can reject the null hypothesis.
P value
Greater than 0.05.
So P value
Less than 0.05.
less than
0.05.
0.05. This means model is heteroscedastic. And if the P value is greater than 0.05, is this clear?
So in the second test, we do this hypothesis testing, right?
You do this together. You first plot and find out from the graph whether your model is hetero or homoscedastic. If the chart is not clear to you, you are not able to make out, then you can do the test. And then compare the chart versus the result. Parallelly, you can do.
So in the first test or the second test?
For both.
For the both.
Because the hypothesis is the same. See, every test go by with some assumptions. So that's why we have so many different tests. We have White's test, we have so many other tests, but don't get into too many hypotheses. One or two is sufficient. Any questions? Yahan tak? Next topic. Now, in a multiple linear regression, we have the equation like this: y equals a plus b1 x1 plus b2 x2 till bn xn. Okay, multiple features. How do you interpret this formula?
Suppose if we consider x1, if the value of x1 increases by 1 unit, then the dependent variable y will increase by the factor of p1.
Very good. There is one more thing that you have to say. Nice answer. When x1 increases by 1 unit, what is the corresponding increase in y? When
All other are kept constant.
correct. When all the others are kept constant. Kept constant means 0. Okay, so this will tell you what is the impact of each feature on the y variable. Okay, if x1 is, let's say y1 is the projected sales. Okay, sales in rupees. Okay, और x1 है production cost. So if production cost increases by 1 unit, what is the corresponding sales? It could be increase or decrease. That depends on the value of B1. So uska impact, how much is it? Okay, that is how you interpret keeping others constant. So if I keep x1 and xn constant, impact of x2 on y. Okay. Was this covered? Interpretation?
Little bit. The formula was given, so with the formula it was.
Okay. Okay. I'm just going through the topics. I don't want to give a haphazard either say shuru kiya, then come here. There has to be a sequence. Okay, so there is just one last thing that you have to remember, how to interpret the summary. When you create a model using the trained data, the first thing you will do is print the summary. And then you will check or validate the assumptions that we discussed some time back. Okay. Or you can do the other way also. You can first check the validations, then summary. But generally, we follow this pattern, create the model, and then summarize the model, then do the assumptions check. Now, what does the summary tell you? आपने किया होगा ना the linear regression model building part. Did you do the summary?
Yeah.
So summary, what all do you see?
Square and adjusted R square were there.
You will see R square, adjusted R square.
Then the list of the features. List of the features along with their p-values and the coefficients.
Okay, good. So you will see the list of features x1, x2, x3, x4. Let's take only 4 features. So the first thing that you will see is, and you will also see the constant term. Okay. The first thing you will see is the coefficient. Okay. ये कोएफिशिएंट क्या है? The A and B values. Okay, so this is the A value, this is the B1, this is B2, this is B3, and this is B4. Then the next thing that you see is standard error. Okay, standard error should be a small value, so not very much significant in terms of interpreting. The ones that you have to focus on is the t statistic and then the p value. And you also get a range, the range of t. Right? And then you have the Epps score, which is the ANOVA score, all the other things. Okay. What is the use of this section? ये किसके लिए है?
It is to analyze which features are significant.
For analyzing the feature significance. Have you been taught how to analyze this and figure out which feature is significant, which is not?
Depending on the p-value. So
do you know how to interpret it?
Yeah, if it is less than 0.05, then the feature is significant.
You have been told that, isn't it? Yes. Should I repeat, should I revise, or you're okay with it? Online? But do you know why less than 0.5 is significant?
Not actually, but we perform hypothesis testing there.
What is a hypothesis?
Prediction.
See, I am saying, I want to check whether the feature X1 is significant. Okay. So I get a t statistic, let's say 2.481. Is this significant?
If it is right to the significance level, then it is significant. I'm not actually recalling that.
That's okay. So okay, I'll put the p value also. Okay, I'll put the p value as 0.00264. Let's say this is the p value, some random number. Is this significant feature or not significant?
Yes, yes.
Why is it significant? Answer is correct. This is a significant feature. But what is the theory behind it? Yeah.
So while doing the hypothesis test, the H0 we are assuming is that P1 value is equal to 0. It means there is no correlation between the X1 and the dependent variable Y.
Right.
And the alternate hypothesis is there is correlation between these two values.
So the null hypothesis is for this feature X1, the B value is 0. And the alternate hypothesis is the B value for X1 is not 0. So assume that B value can take a value 0. What will happen?
No relation between values.
So what happens to the equation? So y hat equals a plus. So this is for feature X1. So when B is 0, what will happen to my equation? A plus 0 plus B2X2. Okay, this B equals to 0 means that B can take a value 0. Okay, it's not that B will always be 0. Can it take a value 0? Yes or no? So if it takes a value 0, it means that the value can take 0 or it cannot take 0. Both can happen. So I am considering that to be insignificant because whether you are there or not doesn't make any difference. You either are not there or you are there. You cannot have both. Okay. So if my null hypothesis is going to be rejected, that means I'm accepting the alternate hypothesis, which means my coefficient can never be 0. Hence, it is significant. Is this clear? That is the reason why we check the summary to find out what is the t-value or the p-value. We can take any one. So if the value of t is greater than 1.645, that is the z-score for 95%. Right-hand side of the number, significant. Or if the value is, p-value is less than 0.05, again, right-hand side, that means reject null, accept alternate. And the same information is shown in the last column where you get a range. That is a confidence interval. So you will get a range something like this. Let's say 0.5 to, let's say 3.9. Now, how do I read the last column?
It is the range of that D1, right?
It is a range. Okay.
D1 can lie between.
So check whether it is ranging from negative to positive. If it is lying from negative to positive, it means insignificant. Why?
It has a 0.
It has a 0. So either it has to lie from negative to negative or positive to positive. So all these are linked to each other. So either take t-stat, or you can analyze with the p-value, or you can take this, because everything will lead to the same conclusion, significant or not significant. Is this theory clear to everyone? This is very important. If you don't understand this, it becomes very difficult for you to do feature selection and other interpretation of your model. Online people, any questions? We are done with the theory part. Okay, so no questions. So that means all good. So we'll do the hands-on in the next session. Do you have any data set with you? Then I'll share the data set, and then we'll do the hands-on session next class.
In Python.
Python, yes, definitely. So in the your previous faculty, how did you do the hands-on?
So he used to do it from by his own, by his end, and then he used to estimate us, and then we
used to write it.
Yes.
Okay, then it's fine. Every person has its own, they have their own way. Some people, they share the code and then explain it on the board. That is one way.
But it used to take a lot of time, because after his explanation, people used to write it by their own. So it was taking a lot of time.
So which method do you prefer?
So the explaining and sharing.
Yeah, so explain and then sharing, because if we find some doubt, then we can ask, we can reach you in the next session.
No, sharing as in bit by bit or the entire code?
Entire code. Entire code.
But will you understand each part of the code? If I have to explain it, that becomes even more difficult.
Yes. So we can do one thing. We can write our code with you only. So you write your code on the screen. You can also explain at the same time, and we can take that code at the same time.
See, I have done all the different ways. I have given the code, then line by line explain. Some people, they prefer that way. Some people, they want it bits and pieces. Explain the first part, then copy paste it on the chat. They will write it. Okay. Then other variety is I'm typing here, you type it here, then we get it. So up to you.
So that part I think is too much time consuming. So we'll take some way where we can reduce much time as possible.
No, I think it should get over in one session.
Okay. Because from the last experience, it was taking a lot of time.
Okay, no issues. Okay, so thank you everyone, people online, and I hope you get well soon. People who are not well, and see you in class next week. Bye bye, and have a good weekend and a good week ahead.